Good morning, everyone. I am just ridiculously excited to be here. And by here, I mean, sadly, here in California. I'm coming to you from the other side of the planet, I think, at this point. Uh, uh, but for folks who don't know me, I'm Chandler Carruth. I work at Google. I'm one of our technical leads working on programming languages. I spend a lot of time working on C++ and compilers and LLVM and optimization. And I'm here to talk a little bit about C++ and maybe what comes next for C++. But I just have to start off because I'm actually really delighted to be able to be here at all. I sadly wasn't able to travel, but talking to the organizers of NDC TechTown, they're just amazing. They were able to put together a virtual presentation, and so I'm able to come to you from the other side of the planet. It's maybe the easiest 9 a.m. talk I've ever had to wake up for because it's midnight here. But that actually means you get me kind of in my prime. I'm kind of a night owl, and so this works well for me in the end. But I really wish I could be there, though. Even if it were in the morning, I really miss the kind of energy of an in-person conference. So I'm going to try and imagine that I'm there, that we've got the whole big audience thing going. And I really appreciate you guys being here so that I can talk to you, because this is a talk that I did give at C++ North, but that's not in Europe. And I was really sad a lot of people I know couldn't make it, and it's something that I really, really want to talk with everyone in the C++ community about. And I was just so excited to have the opportunity to kind of come to this particular audience, get to share it with this audience, and get to kind of get more people to hear what we're talking about, hear what their feedback is, and start a real discussion with you all. And so thank you to all of the audience, and thank you to the organizers for making this happen. I wouldn't have imagined this was possible. I also am going to try and go fairly quickly through the talk because I want to give as much time as I can for kind of Q&A. They have a microphone. I can hear you. It should be pretty easy to actually have a proper Q&A, even with the virtual talk. But apologies if I'm going a little bit fast. If you do need to interrupt me, get a question in, flag down the person with the microphone. I'm happy to pause and try and clarify anything. But unless it's a clarification, let's hold the questions for the end. Write it down. Text it to yourself or something, and we'll grab it at the end. And so with that, let's just dive in. C++. What comes next? And the answer to this is a little surprising. I don't know what comes next. I really don't. This is actually the answer. I hope you weren't expecting a different talk. I don't actually have an answer at the end of the talk. But I think this is a really important question that we need to answer. And so I want to start digging into this question a little bit. And first, we need to understand what it means for a language to come next. Let's look at C going into C++. Right? C++ came after C, added a tremendous amount of functionality. There are other examples. We can look at TypeScript, which came after JavaScript. We can look at Swift, came after Objective-C. Kotlin came after Java. But when we look at C++, there's a real blank here. There isn't this good language that I feel like comes naturally after C++. And I think we need to really figure out what might fit into this. I don't think we're at the end of that journey. I don't think we've got an answer that we can plug in here. So where do we begin answering this question? If I don't know yet, where do we start? Well, I always want to start with the goals, right? I want to start with what problem I'm trying to solve. So what are our goals for C++, and what problem, what programming or software development problem do we use C++ to solve? Titus and myself, Titus Winters, and I gave a long talk really digging into this a few years ago at CPPCon, where we really tried to talk about what is C++, right? What problems do we want it to solve? Have fun watching the talk if you want. It's a super fun talk. We had lots of fun making it, coming up with different ways to get at this idea of what is C++. We also wrote a paper as part of the committee process that really laid out what our goals were for C++, right? We want performance critical software. We need that software in the language it's written in to be able to evolve. We need our code to be easy to read, understand, easy to write. We want practical safety and testing. We need fast and scalable development processes and platforms. We need to be able to support modern operating systems, hardware architectures, environments. Right? This is what we want out of C++. And that really gets to the heart of this question, because at the moment, C++ falls short of these goals. It really isn't where we want it to be. Lots of you in the room can probably think of something that you would like to improve about C++. That if you just had a magic wand, my presentation over one was like, I will make C++ better, right? And it's hard. It's incredibly difficult, right? Like, why is C++ falling behind our goals? There's a huge amount of effort being invested into it. We've worked on it for a long time. Lots of people across the industry have. So understanding the why, I think, is really challenging, and maybe even more important than thinking about specific improvements or specific areas where C++ could be doing better. Why is it struggling? I think there are two core reasons here. First, C++ has accumulated decades of technical debt. And this isn't for bad reasons. It's not like someone made a mistake here. That's not what happened at all. This was done often for the best possible reasons. As an example, a huge part of C++'s success was building directly on top of the existing C ecosystem, right? This gave it access to the dominant software ecosystem at the time. It allowed it to be incredibly more useful to people. But it also meant inheriting the C preprocessor, textual inclusion, C headers, strange integer promotion semantics. I mean, a whole list of things. It meant inheriting a lot of C's technical debt. Now, this was a really well-motivated decision. It was an excellent reason to do this, but it had a very high cost, right? And all of the technical debt that C++ has a very high cost. And it's compounded by the second reason, which is prioritizing backwards compatibility. And again, prioritizing backwards compatibility isn't in and of itself a bad thing. It can be really useful and a huge feature for a lot of people. But it does create a problem, because it means that every time we make a mistake in the language, we can't fix it. We can't even fix easy mistakes. We can't fix them even when they are new, and it would be relatively cheap to do so, because we want to have that backwards compatibility. We also can't fix it when we have tools that could manage the cost of fixing it for developers. We distort new features that we're adding to the language to avoid breaking any legacy code. We have co-await and co-yield and co-return, and I don't know what the next co-keyword will be, but there will be one. And it's all to try and deal with backwards compatibility, right? Every time we do this, we basically take on an ever-growing set of acceptably small increments of technical debt on top of the inherited pile of technical debt. But backwards compatibility does more than that. It also prevents fixing technical debt, because by nature, if you have technical debt and you have Hiram's law, which says that whether you intended it or not, code will depend on every single feature of your implementation. That means code's depending on this technical debt. Someone's holding down their spacebar to warm up their keyboard or something, right? You can't just fix technical debt while maintaining backwards compatibility. These are fundamental tensions, right? In fact, some of the time, backwards compatibility is why we took on the technical debt in the first place. And so this is a really self-reinforcing system. There is another thing that makes it difficult to improve C++, though, which is that the evolution process itself makes improvements extremely difficult. C++ has evolved as part of the standards committee, and this uses a multi-year waterfall committee process. Access is restricted and expensive. You have to attend in person in many cases in order to have a voice. Decisions are made by a live vote of those who happen to be in the room. And a lot of the process, a lot of the aspects of this, it's not like the people running the committee are unaware of the challenges. A lot of this process comes from ISO. And it's not really in our control, right? It's not even in the control of any of the programming languages that are part of ISO. And fundamentally, ISO's process has a reason behind it. It is oriented around ensuring that nations and experts, especially those at companies, have a voice and are represented in discussions and decisions around standards. And I mean, I think that's actually okay, right? That's a valid set of priorities, but it's a very different set of priorities from the ones that I would choose in order to build kind of an effective group for designing an incredibly complex software system. Right? It doesn't prioritize things like being inclusive and welcoming or being a very high productive, very effective team to tackle these complex design challenges. And so I think this compounds the other problems, right? The process itself just compounds all of these other problems. And I think you see some of this reflected in the design, right? We tend to prioritize safe, easy changes to make rather than difficult, maybe expensive changes to make that have higher impact, that might allow us to start paying down this technical debt. And that's just a function of how the process works. But okay, that's enough doom and gloom. What options are there? Like, what is next? Like, where do we actually go from here, right? Especially if improving C++ directly is difficult enough that it's not proving a really effective path. I think the obvious answer for what options we have are existing programming languages. That would be ideal. Programming languages are wildly expensive, especially factoring in the larger ecosystem around them. And so this is where we absolutely should start. A bunch of existing programming languages are fantastic, but are garbage collected. And honestly, garbage collected languages are pretty awesome. I don't know how many folks have used them. They're amazing because they really simplify the programming model. They can be really simple, reliable, safe, easy to use. They're fantastic, right? The challenge is that they have performance gaps, right? They still have some performance gap. Maybe they have a performance gap on throughput, maybe on latency. That there's a huge body of research trying to find better ways to minimize the performance gap. But at the end of the day, they do have a cost, right? They really do have a cost, since they don't often serve in the roles that we're looking to use C++, right? When we look at that priority list, right, performance was at the very top. Now there's another obvious candidate that we should be thinking about, Rust. Now, this isn't a Rust talk. I hate to tell anyone who is thinking this is a Rust talk. That's not anything to do with Rust, though, because frankly, Rust is amazing. If Rust works, you should absolutely use it. It's a fantastic language. I'm super excited to see what they're doing in the community. I'm really impressed by both the language and the community. They're doing an amazing, amazing job. So if Rust is working, please don't get distracted by this talk at all. This isn't for you, right? But there is a problem for some folks in using Rust. And that's that moving a C++ ecosystem, especially a large one, to Rust is very difficult. It's very, very difficult, and it's very, very expensive. Some of my colleagues are actually working on figuring out ways to try and make this easier, to make it a little bit more possible, a little bit more feasible. But it's still early days, and right now the cost is just really difficult for a lot of groups to swallow. Okay, so I don't know of any other existing languages that are really great options here. There are of course many other languages. I could spend a whole talk trying to go through every single language, but none of them seem to really work. And so I think it's useful to kind of look at what approaches have worked in the past. So let's go back to my little list here. We have C to C++, works really great. Java to TypeScript, it works really great. And these are kind of interestingly similar in one respect. Both of these are taking basically a superset approach, right? C++ and TypeScript are supersets of C and JavaScript respectively. And this is a really effective way to kind of take an existing ecosystem and extend it, right? But we also see some different patterns emerging here over time. So Objective-C to Swift is different. It's a more advanced kind of evolutionary path, because Swift has a totally new syntax. It's not a superset of Objective-C syntax at all. And instead it uses compiler technology to provide this interoperability, to provide the path from Objective-C into Swift. And I think we see it even more clearly if we look at Kotlin, which is a very new language, but that's in a lot of ways trying to build on top of the Java ecosystem. And I think Kotlin is a fantastic example of this idea of, instead of following a superset, particularly a syntactic superset approach, really leveraging interoperability and bi-directional interoperability, where you can, Java code can call Kotlin code, and Kotlin code can call Java code. The ergonomics are good. They don't feel like, completely unrelated programming languages. They have, the same core constructs beneath them. And this makes a very compelling adoption path, a very compelling tool-assisted migration path. But it does so with the ability to make pretty significant and dramatic improvements to the language, which can be really difficult with a superset. And when we look at all of these, we start to see a pattern emerging. Each and every one of these was designed for the purpose. They're designed to be a successor language, okay? And I think this is really exciting. So a successor language here is one that builds on an existing ecosystem without bootstrapping a new one. It gives you bidirectional interoperability. You have some optimized learning curve. You can just adopt it pretty easily. And ideally, you can migrate code with tools, not just manually, but actually with tools, migrate code from the old language to the new language. And we see this with Swift, and we see it really compellingly with Kotlin. And this isn't like a new idea either. If you actually watch Herb's Bridge to New Thing talk, you'll see him talking about exactly these different kinds of successor language approaches, both the superset and this more interoperability-based one. But for me, I'm really interested in how we could do something to really dramatically improve C++ and do it through this interoperability successor language approach. And so this is what a group of us have been working on for a couple of years. We've just made it public this year. It's called the Carbon language. And this is basically an experimental successor to C++. So Carbon, where do we start with Carbon? We start the same place we start with C++. We start with goals, right? Carbon's goals as a successor language start off with the same 6 goals as C++. But we add one more goal here that's really critical to make Carbon a successor language: interoperability with and migration from existing C++ code. And there are 3 parts of these goals that are going to be key to be a successful successor language here: interoperability, migration, and language evolution. With interoperability, we don't have to inherit all of the C++ technical debt. This is what separates us from a superset approach, and it allows us to really dramatically start pushing down the technical debt. Migration allows us to provide immediate and dramatic improvements to code, right? And then language evolution is how we sustain this, how we actually keep this kind of improvement going forward. Because without this, we're going to get a single step function improvement, and then we're done. And I don't think that makes any sense. We're going to go through the cost of this. We have to have some path to continually actually refresh the language, keep it really, really effective, keep it meeting developers' needs, even as they change, even as our technology changes. And with the 3 of these, I think we have something pretty exciting. And this is basically our path to avoiding backwards compatibility the way C++ does, to try and use tools to do these upgrades, to do this improvement over time. All right, so let's talk about the language itself. I'm just going to try and introduce you to a few pieces of the language. Based on time, I may have to skim through a little bit, but we can go back and dig into this in more detail if it's useful. Let's go in and just look at a few things. One thing, just as a reminder, right, the Carbon is still in its infancy. We really wanted to make this an open source project very, very early in the project so we could get broad input and a lot of people involved early on. We're incredibly far away from being done. None of this is baked or set in stone. We've got a long, long road ahead of us. And so I don't want you to get over-indexed on this, but I do want to kind of introduce some of the concepts we think we can bring into the language to make something that's going to be more powerful and more appealing for developers. So let's start off with the simple things. Let's start off with syntax. And one of the improvements we'd like to bring in are introducer keywords and a very simple parsing grammar, something that makes the syntax incredibly obvious, incredibly easy to parse, easy to build new tools on top of. But unfortunately, this is kind of the greatest breaking change of them all. Doing this, requires that you're doing something like a tooling-based process. But it also turns out this is where tools are best, right? Tools are really, really good at doing these kinds of upgrades, these kinds of migrations. And the way this looks, if we start looking at some code snippets, is when we declare a new function, we add a little fn keyword at the start of it, and that tells us, oh, we're declaring a function, right? When we're declaring a variable, if my slide updates, eventually. There we go. Declaring a variable, we get a var keyword in there just to try and make sure it's very clear this is a variable declaration. We even do little things because we also want to use name and then a colon followed by a type, because this solves some of the hardest parsing problems. One of the things that I find most frustrating is if you go to Wikipedia, there's an article, the most vexing parse. It doesn't mention C++. The most vexing parse, and it's a C++ example. And that just makes me really sad. And it's actually this thing, it's variable declarations in C++ end up hitting the most vexing parse. And that we don't need to have vexing parses. We can have easy parses for humans, for compilers, for IDEs, for Vim, for Emacs, for every code editor in the world, right? We can make this super, super, super easy. And so talk about some other changes here. Another big change is trying to have a really well-designed way to have function input parameters, or basically read-only values. These are values that you're just reading. You're not going to try and modify them. They're immutable. They don't change anywhere. Because this turns out to be an overwhelming chunk of the code you write. C++ tends to use const references for these, which are kind of good for function inputs, except when that's actually a performance overhead, because they would fit in register, right? Using a const reference for an int is really unfortunate. And that means you kind of have to know for each and every type, well, how do I want to pass it as an input? And it gets worse, because when you're writing a template code, you don't know what type you have. So you just have to take it as a const reference, even when that's a performance overhead. But fixing this is an incredibly disruptive breaking change. It's also a huge opportunity for us. So what does this end up looking like? You have in your parameters, you say that I want a circle, right? This is a parameter named circle. It has the circle type, and this is an input parameter. The default is an input parameter because we think that's the default for functions, right? We have 32-bit integer input parameter, right? And it just works really efficiently. And the compiler, the implementation, is responsible for figuring out what's the most efficient way to pass these parameters, right? We get to really optimize that really nicely for you. But if we have these input parameters, that's nice. We have these values, and we use those for these read-only things. We do need to do mutation. It turns out programs aren't as interesting without mutation. At least for me, I don't think I'm good enough to really do the pure functional programming. It's never been something I can wrap my head around easily. So we want to have mutation, right? And the way we do that is through pointers. Pointers give us both indirect access to objects and mutation. And our whole hope is to try and compress all of that space into a simple construct of pointers. When you compare them to references, pointers are a lot simpler, because with references, you can't really talk about the reference separately from the referenced object, right? You have two things, but you can only talk to one of them. And pointers give you a very natural way of representing that. A lot of languages that have references, modern languages that have references, they actually very explicitly model them as pointers, and use something like automatic dereferencing, because it's so important to be able to separate the two pieces of this. We want to try and preserve that separation and not have 14 different kinds of references either. We want to try and have all of them just be pointers. That said, pointers come with their own problems, which we can fix. We can make pointers always non-null. We can make, we can use some other dedicated tool for things like pointer arithmetic and indexing. That can be a separate tool that has the guardrails you probably want built into it. And that leaves pointers kind of in this very simple, very easy to understand space. And in code, this looks like, we have an output parameter results here, or an input output parameter results here, and that's just passed by pointer. And for me, I really like this because when you have an in-out parameter like this, in some ways it is indirect, right? You're modifying the caller's vector. It's not yours. And we make that very explicit. We have a pointer to the caller's vector. And then in the code, we actually go and modify it. And so it's very clear. This is actually modifying the caller's vector. Another big change is to try and simplify how we name types, especially complicated types. This is particularly important in generic code and in metaprogramming, where we have parameterized type names in interesting ways. In C++, they're kind of two separate grammars that kind of overlap somewhat, but also conflict in various places. Results in a bunch of complexity in parsing, a bunch of complexity in the language. And we try to take a simplifying idea. What if we just say that, no, look, when you try to name a type, that's an expression. It uses the same grammar. You're just naming a compile. You're just writing an expression that expands to a type. One of the consequences is that we already have nice balanced delimiters for passing parameters to types. We have parentheses. And so here you can see we have circled. This is actually an expression, right? It references an identifier, the class type declared earlier. I32 is also an expression, similar to, well, 32, right? Similar to an integer literal. You can have an integer type literal that gives you a 32-bit type. And we have, the more interesting case of vector, which is a parameterized type, and we use normal function-style parameters to pass 32-bit floating point type as a type parameter here. Another thing we've tried to simplify is the root namespace. And so we have, instead of having a single global namespace for all code everywhere, we try to have packages, which are kind of the rough unit of code that would typically be versioned together or distributed together, have its own root in a namespace, and all of the packages have to be named. And this way, there isn't a single top-level namespace. Every top-level namespace is actually local to something you probably control, and that's kind of versioned together and controlled together. And it's given a name for whenever someone else needs to access it. The way this works in code is you start off all of your code saying that, hey, I'm in this geometry package here. And then when you want to go and import an API, now that you have that name, you don't have to textually include the code. You can actually just write import and import the math package. And when you want to use it, you say math.py, right? And the fact that math is in the namespace isn't surprising because you wrote that locally, right? And the fact that you get to pi isn't surprising because you do that inside of math. So there's nothing, from outside of your package that can ever come in and add things to your package's namespace. Your package controls its namespace very, very directly. I'm going to skip some of the other changes here just in the interest of time. And so we also made some changes to how members are declared. They're public by default, so I'm just going to zip through this a little bit. One thing I do want to try and make clear is we have just canonicalized on using an explicit object parameter to declare a method. And so we have, non-methods or like a static member function doesn't have an object parameter here at all. And when we want a method, we add an object parameter. You use a keyword to identify it. I use me here. The use of me here is really weird. Basically, every other language, even including C++ now, that it's getting explicit object parameters, calls itself. We're probably going to change this to also call itself, but when we started off, we were trying to save 2 characters. Probably not worth it. But you have a keyword that says this is the object parameter, and you have a special type for it to kind of model how that parameter works. And this means that this is a method. And because it's an input parameter, it's a read-only method. It can't modify the object that you're calling it on. But you just call it like normally if you have an article, you say as HTML. And then we also have mutating methods, but those need to accept pointers, right? So we have to take the object by pointer because we're going to mutate it, right? And we have a special tool called adder that just says, look, for this method, you need to take the address of the object before you pass it to us. because this is one affordance that if we only use pointers, this would be way too inconvenient to write code. And so this is the big escape hatch that we use here to just cause you to take the address automatically. So as a consequence, you can also just write article.publish. It's just like it would in C++, but it's very explicit this is a mutation and how that mutation works. We do have single inheritance, and classes are default. We have some nice syntax for that, but it's really unsurprising, so I'm just going to zip right through this. Lots of nice keywords. We also have keywords for abstract methods and keywords instead of override. We've tried to just canonicalize on the same set of keywords and make them very clear and in the same position everywhere. Sorry to skip forward, but I want to make sure that we get through everything in time. The last real language topic I want to mention is that we have powerful definition checked generics. And I think this may be the biggest change that we need to bring into Carbon from C++, but I think in some ways it's also one of the most foundational changes we need to make, because today C++ uses templates to do all generic programming. Let's do static polymorphism, very nice low coupling ways of dealing with multiple interfaces. It's great in some ways. Generic programming is fantastic, but using templates has a lot of drawbacks. They're duck typed and they're late bound, right? It means that you can't really type check the template definitions. Even with C++ concepts that we got in C++ 20, you can constrain the template, but you can't fully definition check it. It only partially addresses it. And I think it doesn't really go to the important last step of fundamentally checking the generics fully at their definition time. For example, we can't build dynamic type erasure on top of the C++ 20 concepts we got. So we want to add definition checked generics, very similar to C++ OX concepts, but maybe even more similar to more modern programming languages like Rust's traits and Swift's protocols, which are both also definition checked generics. And this directly addresses a ton of issues with the template system. However, it's particularly challenging for Carbon because we can't just add definition checked generics. We have to interoperate with C++. That means we have definition checked generics that you can extend to templates. And so we fully support C++ templates within this framework with a very smooth evolution path to adopt definition checking for your generic code where you want to. I could spend like a whole talk talking about this. I'm going to give just the very briefest of introduction here. To start off with, we have to define the interface that we want to be generic over, right? And this is called, maybe unsurprisingly, interface. This interface is named summary. It has a method, summarize. The summarize returns a string. Nothing too surprising. And then we can write a generic function, right? And this generic function, print summary, it takes a type parameter, and this is Carbon. The square brackets here are Carbon's deduced parameter syntax. And so this is a deduced type parameter. You cannot pass it explicitly. And because of that exclamation point, it is a generic parameter. It is actually something that has to be done at compile time, not at runtime. And we say that this is a summary type, not just any type, but a summary type. And that uses the interface above. Once we do this, we have this nice generic, and we can do some really, really cool things here, right? We have our x, we pass it with t. This is where we deduce that parameter from. And now we can call x.summarize. And we can type check this when we see the definition. We never need to see the type that implements summary, because the summary interface tells us exactly how to type check this. Right? So this gives us fully type checked definition of a generic function. And when you want to implement an interface, types do that explicitly. It's not automatic the way it is in C++ templates. You have to actually say, I want to implement the summary interface. Okay, and so if we have, say, a news article, right, we can implement summary with this declaration that, hey, look, I want to implement my class as a summary type. Okay, and now I have to define that summarize method. And because this is part of the news article, this is also a method on news article, right? We put it inside of this impl block so that it could be used for the generics mechanism, but it's still a method on news article. So down here, right, I have a function that takes a news article, right? And I can both use that with my generic function because it has this impl as summary, and also directly call it. Make sense? Hopefully. I know I'm going a little bit fast. The last thing that interfaces provide us is a single language extension point mechanism for API design. So instead of using ADL and having some real complexities with overload sets and ADL, we have a much more clearly designed and clearly defined extension point mechanism in the language. We use it for generics, and we use it for everything else that we can, so that we just push all of that work right into this piece of the language. So let's imagine we have some other package of code, right? Someone else's code. This is not our code. This is another package. And we want to implement this summary interface. We can actually do that. We have to say that this isn't an internal impl. We can't change the API of the other package. This is something that's external to it. Right? And so we say external impl, say that that's this other package.tweet, because similar to a news article, you can summarize a tweet. Bit redundant, but we could do that. Right? And once you implement the summary for this tweet, now I can come down into this function, I take a tweet, and I can call my generic function on it. And the reason that I'm allowed to do this is because this is the code that defines the interface summary. So there are two places where you can define these implementations. You can define them with the type, and you can define them with the interface. You can only define them in those two places. And a nice property is that because those are the only two places you can define it, we can actually check that you have a definition. We don't have any no diagnostic required here. We have a definitive check that, like, yes, you implemented summary for this type. We found it. There is exactly one. No other would be possible. There's no link time problem. There's no runtime problem here. Right? So we get something that's a lot more principled and a lot easier to work with for programmers. Okay, I can keep going for a long time, but I need to spend at least a little bit of time talking about one thing that we can't really skip over here. Interop. All of this is nice programming language design. The key to Carbon is C++ interop. So what does this look like? Well, we have to start with some C++ code. So this is boring, right? We've got a struct circle in C++. The magic happens in Carbon, because in Carbon, I can import from C++ code, okay? And what this is going to do is it's going to fire up your C++ compiler, Clang in this case. It's going to go and it's going to parse this C++ header, this circle.h, and it's going to turn it into a Clang header module, right? Implicitly and automatically, and it's going to import that as if it were a module, as if it were part of Carbon itself, right? And then it's going to give you access to the C++ code from within Carbon. So now I can talk about that C++ type circle, right? I can pass it to a Carbon generic here, right? And Carbon's generic or template is going to have to work with C++ types. I can run it through a for loop. I can access members, and I can do math on them. All of the things that you would expect to be able to do with your C++ type, you can just do directly in Carbon. And we do this by kind of compiler-level interoperability that we build into the language. But that's only one direction, and we really need bidirectional interoperability. And so we can go back to C++ code. And in C++ code, we can include a header file. And this isn't a header file that you write. This is something that's provided by Carbon. And we can extend Clang to, under the hood, go and take this Carbon library that we wrote on the left here and turn it into a C++ Clang header module that it can import into your C++ code. It's going to transform all the things and give you access to it. And so now the geometry package in Carbon becomes a namespace in C++. And my print area function is just a function, and I can call it from Carbon. And I can pass my vector of circles to it, and it'll trigger all the implicit conversions and turn it into a Carbon slice and then pass it through, right? The whole goal is to make this just work. So that's kind of how we expect to get interop through. To talk about interoperability, migration, we also need to cover process. So how is Carbon the project going to actually evolve over time successfully. First, and for me foremost, is culture, right? The community and the culture. There's a great quote from Peter Drucker: culture eats strategy for breakfast, technology for lunch, and products for dinner, and soon thereafter, everything else too, right? This is a quote that's gone all the rounds of like the business world and all of that thing. That's where I encountered it. But I think it's actually really true for technology projects and for teams as well. I really, really love this. And so we're prioritizing culture really highly in Carbon. We want to try and have an inclusive, welcoming community. We want to have a friendly and approachable community. We have a very strong, comprehensive code of conduct. We have an open process for governance and for changing Carbon. We make decisions with a clear rationale, especially when they're very difficult trade-offs, when they're challenging things for us to consider. We work super hard on this. We also want to make sure that the project can have, the batteries included tools and ecosystem that programmers expect. We don't want to just ship you, a language design or a language specification. We want to ship you a compiler and a standard library and a user guide and some tooling and some migration tools and update tools and, a linter maybe. And yes, a package manager. But we're getting ahead of ourselves. Eventually, we want to be able to have this. But from the project's perspective, we're setting ourselves up to have a very wide open scope. We don't want to narrow ourselves down. We want to be able to tackle these things in the future. Once we're ready, it's going to be a while. We're nowhere ready yet. We actually don't even have a working compiler yet. I'm going to come back to that. We also want to try and follow a modern open source development model. This we hope looks really familiar to people, makes it really easy for them to get involved, contribute things, to make Carbon better, in little ways and in big ways. We use LLVM's kind of open source licensing model. We use a contributor license agreement to make sure we can fix bugs in it. We use GitHub. We have a real-time chat on Discord. We use Google Docs and Google Meetings and sometimes Zoom and sometimes other things to try and collaborate. One thing you'll notice is we use a lot of technology and a lot of tools to try and collaborate better. We don't try and stick to some kind of common core set of tools. We want to use everything we can to try and make the process better, try and make the project more effective. We also need to have like an actual process for evolving, right? We need some process for improving it. But we've distilled this down to pull requests, GitHub pull requests. That's it. That's the total improvement model. There's nothing more required. We use pull requests for design improvements, for specification, for adding documentation, for implementing things, all of it. Even significant language designs are developed in pull requests. All we do is we add kind of a proposal document to the pull request that spells out the interesting content, the interesting context, why we're making a change, why it's important, all of the alternatives that we've considered, right? And once we have a pull request, we can just use code review and code review like processes to actually, affect this. Who approves all of these pull requests? Well, we have a governance system for that. So the governance system is, again, really simple. By and large, governance is done through code reviews. But if we have a question, if there's a critical decision we need to make, ultimately we have a 3-person group of leads that are responsible for making decisions. It's kind of like, the benevolent dictator for life model, but, scaled up, not a dictator, not for life. But we're going to keep the benevolent part. That part's good. But we don't want to scale it up too much, right? If we get back to a committee, it's not going to be any more efficient. It's going to have all of the problems that we really have with C++ evolution. So we keep it super small. It's just 3 people, myself, Kate Gregory, who's actually, I think, hiding in the back row of the talk if you want to pester her, and Richard Smith are the 3 current leads. And we're even hoping to, over time, have this group of leads rotate. This shouldn't be something that only 3 people can do. We want to have a decent number of people in the project who can take on the responsibility of being a lead and making decisions. But then, after a year or two, take that hat off, relax a bit, take a break from that and do other things within the project. We also want to try and make sure that we keep it as representative as possible. We're going to try and make sure we don't have more than one person from any one organization long term, but we need the project to grow a bit before we can get to that. So all of this is kind of our core governance. We have lots of plans going forward. I'll just briefly mention kind of where Carbon is at today. We actually have a bunch of contributors to Carbon already. This slide is actually out of date. This was from July before we actually made it public. But like if I regenerate it, you can't read anything. We've got like another 10 plus people who've been helping us out in the open source project. You know, our current focus and roadmap was going public, trying to complete the core language design, and trying to get a demo implementation of that core language design. Speaking of demo implementations, what's our demo implementation? I said we don't have a real compiler. What we have is something else. We have is something that's not an implementation, but kind of like it's an interpreter that you can kind of put code into, and you can see how it would behave if you ran it through, if you actually executed that code. It's an abstract interpreter that just models the semantics of the Carbon language. And one of the people that's been helping out on Carbon is actually Matt Godbolt. And so when we were looking at the design of this, we actually realized that it resembles something that we're probably all familiar with, Compiler Explorer. And we actually call this the Carbon Explorer now with his encouragement. And so this basically lets us explore what Carbon code would look like, understand the semantics, and it's also designed to be really easy to prototype things, really easy to extend and play with new features. And so that's kind of our platform that we're exploring the implementation in right now. And I will briefly see if we can get the live demo to actually work here. Hopefully you all can see. So if you go to carbon.compilerexplorer.com, it's live. You can go there. You can find this example, right? If I remove my X here, right, I'm going to get a compilation error because I don't have good syntax. I can add the X back. If I had more time, I'd happy to do lots more kind of demos. One thing that you'll see here on the right-hand side, it isn't assembly because this is this interpreter. And so what you'll see once you get past all the code snippets, there's a lot of code snippets. Here we go. What you'll start to see here is an actual log of the Compiler Explorer implementing Carbon. And so it begins type checking everything. And it begins, processing declarations and type checking those. And you can go through the different steps as it walks through every single step of evaluating each compile time expression that names each type, that's part of the type checker, right? You can watch each and every step of the semantics actually get implemented in the Explorer, which is super, super nice for understanding very subtle details of how the language semantics work. It's really cool. Feel free to check it out and explore it. It's a fun little project, and it gives us a really great way to understand Carbon and understand how it works. But we haven't actually answered our question. What comes next for C++? Well, I still don't know, right? C++ is probably a big part of what comes next for C++. A lot of users genuinely need backwards compatibility, and there are a lot of good reasons to keep trying to improve C++. I don't want anyone to stop doing that. We also should probably be using garbage collected languages more often. They're great programming environments for people. So if you can, you should use them. And if you can use Rust, you should use Rust. That's fantastic. So the real question for me is Carbon a part of what comes next for C++? And I don't even know the answer to this. I don't think I can answer this. I actually need all of you. I need all of the C++ community to come and help us answer this, right? And so this talk and really the whole Carbon project is, our whole goal is to together find out whether something like Carbon, a programming language like Carbon, is a part of what comes next for C++. I hope that you're interested. I try to go through this as fast as I can, but if hopefully we can do at least a few questions, and I really hope to see all of you on the Discord maybe, or at least like going through the GitHub, trying things out, giving us feedback, and keeping an eye on the project, because we've still got a long road to walk here. We're just getting started with the design. We're just getting started with this Explorer. We're going to have years of work in front of us just to explore this experiment, understand whether this is something that makes sense. And thank you again for having me all the way over in Norway. Questions?
One of the things you said, Rust is fantastic. One little feature I think that I'm missing in C++ is destructive move semantics. And
Yes.
I've been told C++ will probably never have that. But is that something you can have?
It's a great question. So the question is, can we have destructive move semantics? And I think the answer is mostly yes, but it is really hard. And the reason it's really hard is because of C++, right? The people who are saying we can't get into C++, I think they have a point. It's really difficult to graft destructive move semantics onto C++. There's also some other subtle details here, but this is actually part of Carbon that is designed. If you go and search on Carbon's design docs for, there's a proposal about unformed objects and initialization, and it talks about the idea of destructive move and how we're hoping to kind of get the best balance we can between destructive moves like you have in Rust and where C++ is coming from.
Thank you very much.
What about reflection?
What about reflection? Great question. I would love for us to do good reflection, and we're trying to set ourselves up for this using expressions as the core grammar for talking about types. Kind of sets you up to do things like call methods on type objects and do very reflection-y kinds of things with an incredibly natural syntax. And so I'm hoping that we're set up very effectively for this. It's something we're thinking a lot about. However, we've got to walk before we run. We've got to, or I don't know what the right analogy is here. We're like, we've got to have cell division before we can build like an organized life form with like an intelligence and start reflecting on it. We're way earlier stages. And so as we get the core language in place, we're hoping we're leaving good kind of foundations to build reflection on. But actually building reflection and building metaprogramming, I think, is something that we're going to have to invest in the future.
My main interest in reflection is messaging, and there's a lot of things about reflection, like calling internal function, etc., which isn't that interesting. But when it comes where I really miss reflection is messaging, being able to send struct of some kind to another place.
Yes. So I actually think this is not reflection. I think that having some kind of serializable and deserializable way to work with data structures is something that should be baked directly into the language. You shouldn't need even reflection for that. We should have a first-class feature in the programming language designed around how to kind of move data around when you don't have kind of a single address space with a single ABI and everything in memory and no threads or anything like that. But when you have the more complex cases. And so actually we're hoping to add that as kind of a core language feature for Carbon that kind of directly addresses those use cases. But again, early stages, this is like an idea in someone's head. So I don't think we've actually gotten it implemented yet.
Hello. So I'm curious, how would you maintain interoperability with C++ as it continues to evolve in C++ 23, 26, etc.?
On. Yes. So how do we interoperate with an ever larger and moving target of C++? Well, the first step is we have to cheat a little bit. So we don't need to interoperate with all possible C++. We need to operate with real C++ that exists in the world. That helps us a little bit, though, not a lot, because there's a lot of C++ in the world. So the other big thing that we're relying on is we're going to build our interoperability on top of an existing compiler. We're primarily targeting Clang, although there's nothing necessary about Clang in that. But the idea is that if you take a working C++ compiler that has support for these different features, then we can build interoperability on top of that compiler and reuse the amazing amount of work that the Clang community does to kind of keep up with the standards for our interoperability story. If we didn't do that, I don't think we could possibly do this. But that's the fundamental idea, is that we have to keep up. We have to keep, every time new features come into Clang and people start using them, we have to figure out how to interoperate them and map them effectively back into Carbon. To a certain extent, though, if C++ is moving faster than we can move in Carbon, then we've actually answered the experimental question of Carbon, right? Because then this isn't a more effective evolution process and evolution strategy. And so to a certain extent, a core thesis of this experiment is that we think we can keep up with C++. And we'll learn one way or the other.
One of the things that was mentioned is that in C++, one of the things that can hold it back is the backwards compatibility. And how would that be administered in Carbon? Would you have different Carbon versions that would not interoperate with one another, or would you also keep backwards compatibility in Carbon?
Great question. So the whole idea around kind of language evolution within Carbon is this idea of tool-assisted upgrades. And so we don't want to try and have backwards compatibility in Carbon. We think we'd end up exactly like facing very similar and analogous technical challenges that C++ faces. Instead, we'd like to try and have tools, and both in the language itself, language constructs, and actual tools that developers can use to handle the incremental migration. So what we've observed is that whenever you're updating from an old programming language version to a new one, at a certain scale, if you have enough code, this is not a no-up. There's some breaking change, because at the very least, you need a new version of your compiler. And in our experience, every new version of the compiler, some small things have changed enough that there is a cost. We have to modify some code in order to make those updates. And what we want to do is we want to try and build tools and an automation and language features that just dramatically scale up the kinds of changes that people can afford to take when they're ready to do an upgrade. This is fairly similar to Rust's epochs, if you're familiar with them, where they try, or not epochs anymore, they're editions, I think. I forget which name they've picked for them, but they have milestones that they try and target, and you know when you're going to upgrade and see like major and significant changes to the language. You can plan for it. There's a period of time where you can kind of manage the migration of your source code from the old version to the new. We think we can give people these kinds of tools so that they can actually do the upgrade, and they have enough interoperability between versions to do the upgrade. But they are going to have to keep moving, because if we don't do that, we don't get to really solve these problems.
Okay, I think that's it.
That's it. Well, thank all of you again so much for having me, especially from the other side of the planet. It's been a real pleasure to be able to actually talk to you even a little bit. And if you have more questions or you're interested in the project, please get on the GitHub and join the Discord. You can join the Discord and ping me directly there, or just ask the community. I'd love to have you, and I'd love to have more questions. So thank you again.